Hi there. This is part two on the lecture properties of dimension. So let's remember that we're discussing some applications of this theorem in which we assume that we know the dimension of the given vector space, and we're considering a set with a finite number of elements in that set, and then there are implications in which we can find a basis for this vector space, or we can imply information about the property of being linearly dependent or linearly independent. So this theorem is something that relates to properties on dependence, and it relates on properties about spanning, and therefore establishes connections with sets that can be considered a basis for the vector space. So let's now turn our attention on the vector space P sub 4. These are polynomials of degree 4, which in general, let's say here in general, these polynomials will be described as something that looks like a x4, b x3, c x2, d x, and e, right? So we can write a polynomial of degree 4 with 1, 2, 3, 4, 5 coefficients. E really is a coefficient, but it's multiplying the power x to the 0. D multiplies the power x to the 1. So this would be a member of P sub 4, this being a general way of describing a polynomial with a polynomial which has the largest power being x to the 4. Now, for P sub 4, there is a standard basis to describe the elements of this vector space of polynomials, but here we are discussing another. Here we have a set that has that's another basis, okay? And this would be a basis for a subspace of P4. This subspace is denoted as W, and W contains polynomials of degree 4 with one of the roots being the number 2. So when those polynomials are evaluated at 2, they are equal to 0. So you may remember as this being a case study, something that we had analyzed before. And because this set presented here has 4 elements, so these things are listed here separated by comma. So the first element is x minus 2. The second element is this polynomial of degree 2. Then there is an element that has degree 3. And then the last one is this polynomial of degree 4. There are 4 elements in B. B is linearly independent and spanning. And so we conclude that the dimension of the subspace equals 4. So let's see what else can we do. Let's now consider a subset of W. So we would need to check that this subset of W, that this indeed is a subset of W. What is the requirement to be a member of W? Well, you have to have 2 as a root. So you are supposed to check this for every element in this set, but let me just refer to the first element here. So what happens if we evaluate that expression, 3 times the square of something minus 5 times that something minus 2. Let's evaluate this at 2. So this would be 2 squared multiplied by 3, 5 multiplied by 2, and this is looking like 3 times 4, which is 3 times 4 minus 10 minus 2, and here we get 12 minus 12, which is 0. So indeed, this expression, when evaluated at 0, equals 0, and that's precisely what is needed for that polynomial to be to have 2 as a root, and to also be considered a polynomial degree 4 by adding some extra coefficients there. So you can verify that the other elements of this set are also members of W, and it's not too difficult also to verify that this set is linearly independent. So the other thing that is left to you as an exercise is to check linear independence, but to do so, you write a relation of linear dependence. So write the elements of this set and write a linear combination involving those elements. So here is this linear combination with coefficients alpha 1, alpha 2, and alpha 3. And this is a relation of linear dependence, which means the linear combination equals 0. But notice that this 0 here on the right side of the equation, that would be the 0 in P4. Okay, so that 0 in P4 on the right side of the equation, here on the right side of the equation, 0 in P4 means 0 times x4, 0 times x3, 0 times x squared, 0 times x plus 0. So when you work your way on the left side of this relation of linear dependence and you equate the left side to the right side, you're going to end up using the definition of equality in P sub 4, which will imply that you'll have to equate each of the polynomials, each of the coefficients corresponding to each corresponding power, okay? And that will lead to a set of equations that you can solve with RREF and as a set of equations that will be considered a linear system of equations. So in this case, we have checked that this set is linearly independent, and then we can use the theorem to establish that because the dimension of the subspace is 4 and the number of elements in this set is 3, so here there are 3 members or 3 elements, okay, because there is not a match on the dimensionality of the subspace and the number of elements, then the theorem establishes that this set cannot have the spanning property. It cannot span W. Therefore, even though it is linearly independent, it doesn't have the spanning property. It's not a candidate for being a basis. It is not possible to obtain a basis out of a set with 3 elements when the dimension, a basis for W, the subspace, is not possible to have a basis with 3 elements when the dimension of the subspace is 4. Okay, there is a mismatch there. There is a requirement. The dimension of the subspace is 4. Therefore, any basis, the basis is not unique. You may have multiple bases for one vector space. However, the number of elements must be the same even when the sets, each of which is considered a basis, are not identical. They're not the same, but the number of elements must be the same to preserve the dimensionality of the subspace. So here's another theorem that relates to properties of dimension. We consider a rectangular matrix, and we find that the rank of the matrix is exactly equal to the rank of the transpose of the matrix. To illustrate this theorem, we consider a matrix in archetype I. Okay, archetype I, not archetype 1. This matrix has RREF that is displayed here. Therefore, we would conclude that here R equals 3. Okay, R equals 3, and this matrix has 2, 4, 6, 7, right? It has 7 columns, so n equals 7. The rank of this matrix is 3. Also, if we transpose the matrix and find the RREF of the transpose, we obtain precisely that, again, the rank R for the transpose is equal to 3. So the rank of the transpose is also 3, and that is illustrating what the theorem is telling us, that the rank of the original matrix matches the rank of the transpose of the matrix. So this theorem is referring to the dimension of the column space and the dimension of the null space. The dimension of the column space is what we are calling the rank of the matrix. So this is the rank of the matrix, the dimension of the column space, and this is referring to a matrix that has n columns. Okay, n is the number of columns on the matrix. R, little r, is the number of leading ones on the RREF of the matrix, which is denoted here by the matrix B. And so R is considered also the dimensionality of the column space. So if we were going to compute a basis for the column space by looking at the RREF, we know right off the bat that the number of elements on that basis has to be R, because the dimension of the column space, according to this theorem, is given by the number of leading ones on the RREF. And also, the dimension of the null space is going to be the supplement. So that calculation of n minus r, this is kind of carrying on from an old calculation. We were able to compute from a long time ago a basis, a linearly independent set and a spanning set for the null space, and we were always guided by this quantity n minus r, because we learned how to compute vectors z1, z2, all the way through z sub n minus r. So n minus r was always something we use in the background to refer as to how many vectors we will build or construct to describe a linearly independent set and a spanning set for the null space. And that number of vectors is, and it has been for a while, n minus r. So the cool thing is, if you believe me that this is cool, is that n minus r plus r equals n. Well, that you think is trivial, right? But this is no other thing that the dimension of the null space of the matrix added to the dimension of the column space of the matrix. Okay, the dimension of the column space. And those two dimensions always add up to the number of columns of the matrix, right? So this is the composition of n as r plus n minus r. This is a big deal. This dimensionality of the null space is gonna have a name. So here we see that nullity plus the dimensionality of the null space is usually called nullity, and dimension of the column space is called rank. So the nullity plus the rank equals the number of columns, equals n, which is the number of columns on the matrix. Okay, so dimension of null space, dimension of column space, they are a big deal. They are a big deal. The dimension of the null space is called the nullity. Dimension of the column space is called the rank. And similarly, dimensionality of the row space. Remember, the row space is the column space of the transpose. And by something we learn in this lecture, it so happens that the dimension of the column space and dimension of the row space, they are all equal to the same number. And this L of A here, that's called the left null space. All right, and so I'll let you read more carefully and assimilate that 3 and 4 are directly related, are consistent with 1 and 2.